Have you ever looked at a piece of gold jewelry and wondered, where did this come from? Not just the shop or the mine, but way back in time. What if I told you that some of the gold on Earth may have been forged in one of the universe's most violent and mysterious objects, something called a magnetar? Sounds like science fiction, right? But it's actually a theory backed by cutting-edge research. A new study published in the Astrophysical Journal suggests that magnetars, supermagnetic remnants of massive stars, may have played a crucial role in bringing precious metals like gold to Earth long before the solar system even existed. Let's dive into this cosmic mystery and break it down piece by piece. First, what exactly is a magnetar? Magnetars are a type of neutron star, which are incredibly dense remnants left behind after a massive star explodes in a supernova. To give you an idea of just how dense, a single teaspoon of neutron star material would weigh about 1 billion tons. Now, magnetars take that to the next level. They're neutron stars with magnetic fields 1,000 times stronger than typical neutron stars, and a quadrillion times stronger than Earth's magnetic field. To put it simply, magnetars are the universe's ultimate magnets. If one were as close to Earth as the moon, it would wipe the data from every credit card on the planet, just from its magnetic field. Scary stuff. But beyond their terrifying power, magnetars might also be cosmic alchemists. You see, the formation of heavy elements like gold, platinum, and uranium requires conditions of extreme energy. Regular stars can't make them. Even our own sun, as powerful as it is, doesn't come close to the pressure and energy needed to fuse elements heavier than iron. So where do these elements come from? For a long time, scientists believed that these precious metals were primarily created in supernovae or during the collision of neutron stars, and that's still true. In fact, the 2017 observation of 2 neutron stars merging, captured both through telescopes and gravitational wave detectors, was a huge breakthrough in proving that such collisions produce heavy elements. But here's where the new research shakes things up. Scientists now believe that magnetars, which can form after such mergers or even after some types of supernovae, might be responsible for an even larger share of heavy element production than previously thought. In particular, the extreme magnetic fields of magnetars may help create conditions even more favorable for heavy element synthesis. When a neutron star is born with an exceptionally strong magnetic field, the matter ejected from it during and after its birth can undergo what's called rapid neutron capture, or the R process. The R process is essential for creating the heaviest elements in the periodic table. It happens when atomic nuclei rapidly absorb neutrons before they can decay. And for that to happen, you need a crazy amount of energy, and an even crazier number of free neutrons. Enter the magnetar. Its magnetic field, rotational energy, and the extreme conditions around it combine to make it a perfect site for the R process. In some models, just one magnetar-forming event can produce enough gold and other heavy elements to account for entire galactic stocks of these materials. But how does that material get to Earth? Well, after these elements are formed, they don't just vanish. They're blasted into space, mixing with the interstellar dust and gas that eventually comes together to form new stars and planets. Our solar system, which formed about 4.6 billion years ago, was born from one such cloud, containing not only hydrogen and helium, but also a sprinkling of heavier elements formed in long-gone cosmic events. So, the gold in your wedding ring, the platinum in your phone, they may be cosmic souvenirs from a magnetar explosion billions of years ago, in a part of the galaxy we may never even see. This idea isn't just poetic, it's backed by real data. Researchers analyzing the composition of ancient meteorites and the Earth's crust have found isotopic signatures that suggest a major influx of our process materials before the solar system formed. These signatures don't match what we'd expect from typical supernovae alone, but when magnetars are added to the equation, the math starts to work. And this opens up fascinating possibilities. It suggests that some of the most valuable and rare materials on Earth might not be terrestrial at all, but the result of ancient, distant cosmic cataclysms. It's a humbling thought, isn't it? That the stuff we value most, not just gold but also uranium used in nuclear power and even elements critical to modern technology, might owe their existence to stars dying in spectacular fashion. And magnetars are still out there. They're rare, but astronomers estimate there are about 30 million neutron stars in our galaxy, and roughly 10% of those may be magnetars. We've detected only a few dozen so far, mostly because they don't emit light in ways that are easy to spot. Some magnetars reveal themselves through sudden, intense bursts of X-rays or gamma rays. Others remain silent, their magnetic fields slowly decaying over thousands of years. Interestingly, magnetars might also help us solve other space mysteries. For example, they're currently a top candidate explanation for fast radio bursts. Those brief, powerful flashes of radio waves from deep space that we still don't fully understand. So, not only could they be the key to explaining the origins of gold, but they might also help unlock the secrets of the universe itself. And here's the kicker. Because magnetars are so hard to detect, and their birth events are so rare, it's entirely possible that our galaxy, and even nearby galaxies, are littered with ancient remnants of magnetar explosions. They're hiding in plain sight, their heavy element debris scattered across space, woven into the very fabric of planets like ours. It makes you look at everyday things differently, doesn't it? That gold chain, a relic of a stellar apocalypse. Your smartphone, running on materials forged in cosmic furnaces beyond human comprehension. And while we're only just beginning to understand these processes, each new study brings us closer to answering some of the biggest questions in science. Where do we come from? What are we made of? And what role did the most extreme objects in the universe play in shaping our world? Thanks to magnetars, we're learning that the story of Earth is deeply connected to the life and death of stars. And that perhaps is the most precious discovery of all.